So today what I want to be talking about is the differences between model data and pipeline parallelism. So these are both three different parallelism paradigms that are popular to scale large models. What I've always found interesting about these techniques is that people often think like, oh, like you can just scale a large model, by just changing a couple parameters, like having 100 layers instead of five, and then you just like, click, you just go Python large model.py. But the reality is like these larger models bring with themselves like their own set of systems challenges, which also have some very interesting motivating math for how to do it correctly. And so I think just saying it's simple to scale large models is just like a total, so it's very deceptive. It's almost nonsensical. And so I thought today we could talk about how this is done with a specific paper I'm really interested in and happy to be presenting called PipeDream. So this is a paper by a bunch of people at MSR, CMU, and Stanford. And so I think it's a great paper. So we'll just use it as a sort of baseline to discuss these topics. And as always, if you have any questions, feel free to interrupt me in chat and we can go over. So without further ado, let's just get started. All right. So so this is the paper. So it's called PipeDream. And it talks about it's a fast and efficient pipeline parallel DNN training. Uh, so just like maybe at a high level, like what's a pipeline, right? So like before we talk about neural networks or anything like that, you can imagine like let's say you want to just do something like assemble letters, right? And so you basically divide this into a couple of tasks. Like let's say task number one is put paper and letter. Task number two, it's close letter. Task number three is put stamp. Task number four is mail letter. So what's sort of interesting, about this setting is that you can't just do all of these things in parallel. You have to basically wait, like before you close the letter, the paper has to be inside before. Like let's say with putting a stamp, maybe this doesn't matter, but certainly when it comes to mailing the letter, all of this needs to be done beforehand. Also, the task scales. Like basically the parallelism scales with the number of tasks, right? Like if you were to have actually, yeah, let's think about this. Like, yeah. So let's say you were to say, oh, I want two people to mail the letter, for example. Then you could say, well, maybe the utilization is faster or whatever. Like we'll sort of get into this, but at a high level, you can sort of think of every task as necessitating like one person. um, and they can each of these people can specialize it like in each of these tasks. So it's sort of like the logic behind like some supply chains and stuff. If you think of like I don't know those like movies about the industrial revolution and stuff like that. Um, but yeah, like I mean, why are we talking? Like, why are we even talking about pipelining, right? Like, so typically when we talk about parallelism in ML, there's sort of two notions that come up. Like we have data parallelism, we have model parallelism. But now I'm saying like we also have pipelining, right? And so I explained that at a high level, but I definitely want to tie this back to neural networks more specifically. I mean, yeah. So let's just without further ado, we can get started. This is sort of all the background you need. So PipeDream is a deep neural network that parallels computations by pipelining across multiple machines, avoids the slowdowns faced by data parallel training on large models, or limiting network bandwidth induce high communication to computation ratio. Yeah, let's talk about this for a sec. So imagine that like you have four networks that you're training independently on four data sets. Sorry, on so this is like I'm gonna call this model one, this is model two, model three, model four. And you have some data, right? Like here. And the idea behind like data parallel is that, well, it's just really slow for us to pass all of this data throughout the same model because we're limited by disk speed and RAM speed to be or like sorry disk speed in the case where everything doesn't fit in RAM or RAM speed in case it doesn't. In both cases, like this is all going to be slow. And so you end up making four copies of this data and you pass it to the four different versions of your model. Uh, But how does this work then? Like, well, you may say, well, but if they're trained on different subsets of the model, then of the data, then the models are going to be different. And in fact, yes, they will. And so one way to solve this is to basically either synchronize the weights or pass gradients to everyone, right? So basically, like let's say here, there's some gradient updates to the weights. You pass them to all the models. So this model communicates to all four, or this model communicates to some central store, and then that central store communicates to everyone. Or you synchronize the weights directly. In both cases, you're basically here, you have network issues because you have to uh, like you have to actually send these over the wire. And in the case of sync weights, like you have a network, but you also have a sync cost because if you're waiting for the updates from every mini batch, that means that before you go on to the next one, you want to make sure that you're synced to everyone else, or else you're going to be further and further apart. And so this is just sort of like two reasons why, even though on paper data parallelism sounds great to speed up model, like in practice it does end up being more challenging to actually see these speed ups in practice. So it reduces communication by up to 95% for large DNNs relative to data parallel training. I see. So they're just like eliminating the sync problem with these pipelines, and allows perfect overlap of communication and computation, right? So let's just talk about this for a second. Like why is it that basically, oops, uh, like why is it that communication is greater than computation, right? Well, one of the reasons is that GPUs are getting better, right? Like basically every generation, GPUs are so yeah. So every generation's GPUs get a lot better, but the internet doesn't get that much faster, right? Like internet, uh, not much faster. And again, like you're talking about orders of magnitude worth of difference. Like here in this case, let's assume like we're comparing RAM speed versus like we're comparing RAM speed versus network speeds. And just as a sort of sanity check here, like imagine that like you uploading some data, like let's say you uploading a video to YouTube is a lot more time consuming than editing the video directly. And this is sort of a function of that, and that communication costs are generally higher than computation costs. And so part of the design and these parallel techniques is sort of to figure out, well, how can you reduce this communication cost as much as possible and make sure you're actually bottlenecked by your computation. That, like, I mean, you'll probably never actually be bottlenecked by your computation in this case, unless there's absolutely no communication. In which case, this is like here we get to regimes like local updates and stuff. But if you have no communication at all, then you're going to be bottlenecked by computation. But if you have some form of communication, then you're probably going to be bottlenecked by computation, by communication. So how can you reduce the communication overhead as much as possible? And here they're saying they're reducing it by 95%, but not quite why yet. Like we'll get to that. So it keeps all available GPUs productive by systematically partitioning DNN layers among them to balance work and minimize communication. So it versions model parameters for backward pass correctness, and it schedules the forward and backward passes in a round robin fashion to optimize time to target accuracy. And experiments show with 5 different DNNs on 2 different clusters that PipeDream is 5x faster to accuracy than data parallel training. Okay, there's a few ideas here. Uh, so first one here is that here we're talking 5x speed up, right? And then here we're also talking about some sort of round robin algorithm to do the scheduling. We're also saying that it's partitioning DNN layers to balance work and minimize communication. So the minimize communication part, like let's get to in a second. because like I'm not sure how they do it exactly in this paper, but for the balanced work part, I can tell you how this sort of works now. So imagine that you have a large model, right? Something that looks like this. And this model has like these three layers, right? Actually, maybe I should do this. So this is very typical in neural networks. Like imagine like this is an image, and then here this is a classification. What I mean by it's very common is that the beginning layers are large. It's like proportional to the size of your input image. But the output is small because it's just like a binary value or like a categorical value, like determining some sort of classification. And so let's say if you were to sort of naively partition this, like let's say this is like this doesn't fit in memory, let's say. So a naive way to partition it is to come in and say, okay, I want to put this on its own machine. I want to put this on its own machine. And I want to put this on its own machine. So this becomes like this, like machine one, machine two, machine three. The problem with this approach is that machine one is slower. Machine one is slower than machine three, quite a bit slower actually. And so a natural question is to figure out, well, like how can you make the computation more balanced? Like one way, for example, is to just not do this kind of allocation. Like it would be like make sure when you're splitting layers that they're all relatively equal, and it is possible to split up layers and then concatenate them again. So that's fine. But let's say you don't want to do that. Like another technique could be, well, for M3, let's say it's twice. Let's say M3 is twice as fast as M1. Then you would feed M3 twice the amount of data at once. And so here again, like even though you're feeding more, like basically use data parallelism as a like load balancing technique almost. All right. Sorry, just grabbing some coffee. All right. Um, all right. So I mean, let's see. Like this all sounds very cool theoretically. Like we've talked about model parallelism, we've talked about data parallelism, we've talked about the respective issues. I also have another video just about this where I actually show you code. So if that's interesting, it's also on YouTube. It's just called Model versus Data Parallelism, and you'll see like the briefest possible explanations you can find about the topic. So in the last 5 years, neural networks are great. They do everything, and so the such growth only the already time and resource intensive DNN training process, but also causes the commonly used parallelization approaches to break down. So the most common approach is data parallelism, where the DNN model is replicated on multiple worker machines, with each worker processing a subset of the training data. So weight updates computed on individual work are then aggregated to compute a final weight update that reflects updates across all inputs. Yeah, so this is sort of like we talked about this earlier, where either you sync the weights or you sync the gradients. Like for all intents and purposes, like these are sort of the same. Like the dimensionality of the data is similar. Um, it's just like yeah. So I mean, fundamentally, I don't think there's a huge difference in between them, but there's probably some subtle differences I'm not aware of. So the amount of data communicated per aggregation is proportional to the size of the model. Yeah, exactly. So if you're dealing with a huge model, that means you're sending like models that are gigabytes or terabytes in size over your network. And like let's say just within the example of I want to just upload a single YouTube video. It's like let's say this video right here. It's like an hour long. I want to update it to YouTube. That takes about an hour and a half in of itself. So that's not something you wanna deal with. So first, growing model size increases per aggregation communication. Some widely used models are large enough that the communication cost already eclipses the computation time. So limiting scaling and total computation time. So rapid increases in GPU capacity further shift the bottleneck of training towards communication across models. Yeah, so this is basically uh, they're saying like for large models, so communication is greater than computation. All right, I'm just gonna make my head a bit smaller so we can see more of the paper. Does it look better? Okay, excellent. So another approach to distributed training is model parallelism, used traditionally for models that are too large to keep in a worker's memory or cache during training. So it involves training such that each worker evaluates and performs updates for only a subset of the model's parameters. However, even though model parallelism enables training a very large model, traditional model parallelism can lead to severe underutilization of computer resources since it actively uses only one worker at a time. So if each layer is assigned to a worker, it cannot overlap communication computation. If each layer is partitioned, in addition, determining how to best partition a GNN model is challenging. All right, so back to this example here. So we have an input image and we have a classification. Let's say this doesn't fit in memory, we can partition it per layer, but that's definitely not efficient. So then the natural question is, what is an efficient way to do it? And so this ends up being actually, I think, a pretty tricky question because it almost becomes a sort of like convex optimization problem where you're saying like, I want to minimize, speed, like, sorry, uh, I want to minimize training time such that compute budget is less than X and storage budget. Let me put this here. Like, I think I'll draw it nicer here. So basically, model parallelism uh, as a convex optimization problem. All right, what does this mean? So typically, like you want to say something like, well, I want to minimize training time such that compute budget is less than X, storage budget is less than Y, and then network budget is less than Z. So this is sort of I think, a fairly different way of viewing this stuff, but because like you can kind of give it this formulation, uh, this basically like the solution, like to this, like this, let's put this here. So the solution is basically like an optimal uh, data, sorry, model parallelism allocation. As in, like, what is the best way to put like to put different subparts of a network such that you can keep sure that your compute budget is under X, Y, and Z. This is a hard problem, right? Because like you don't even know like typically X, Y, and Z would be determined by your budget. Like this is actually how much you can afford, so it's sort of a business consideration. But in this case, like let's say you want to say, well, I'm fine having a bit more budget, compute budget, but storage, I don't want to have too much more storage. These are functions of each other, right? Like storage budget is also just a function of network budget, so maybe these can be reduced to the same one. Uh, but also similarly, like I mean, while compute budget is not directly like is not equivalent to storage budget, like the more weights you have in your model, the longer computation takes, and then the more that takes to store. The only exception being reversible models, so that's sort of a model that doesn't fit this regime. But you get the point. Like this sort of gets fairly hairy. All right. So back to the paper. So it describes PipeDream, but unlike traditional model parallelism, PipeDream aggressively pipelines mini batch processing with different workers processing different inputs at any instant of time. So this is accomplished by injecting multiple inputs into the worker with the first DNN layer, uh, thereby keeping the pipeline full and ensuring concurrent processing on all workers. It also uses data parallelism for a selected subset of layers to balance computational load among workers. So we refer to this combination of pipelining, model parallelism, and data parallelism as pipeline parallel training. So this is a good point here. So like, what are we talking about here? So basically, you have this, let's say your problem is, let's go back here. Like your initial problem is my model training is slow. And there's sort of three ways, like three dials you can adjust, right? You can say, oh, let me do some data parallelism. Let me do some model parallelism. And then, but so this works, right? This doesn't, like, at least out of the box, uh, just because um, like it model parallelism, like the main purpose of it is really to make models fit. It's not necessarily to make them fast. And so this is where pipelining comes in. With pipelining, basically it's a technique to make model parallelism fast, right? And but actually it's sort of also another thing, right? It's a technique to make model parallelism fast, and it basically makes sure that devices are utilized by using uh, batching uh, differently across uh, blocks or layers. So blocks is just like, it's a different terminology for, maybe you have a group of layers, they're all in the same block, then you would batch everything to that block. This is sort of where stuff like data locality matters. Like, let's say if you're doing, uh, yeah. So basically, like, let's say you have, I mean, yeah, let me just give you an example of this. I mean, so let's say in this case, you have like layer one, and then you have layer two, and you have layer three. All right, well, layer one and layer two, uh, like layer one doesn't care about the weights at layer three, right? So you could put these in the same block together. And then layer three only cares about the, like during backprop at least, it only cares about the value at layer four. And then during forward prop, it only cares about the layers at layer two. So if backprop is causing like more, if the computation time of backprop is lower than the communication cost, then you could, put these like this in a block like this. And then the second consideration here is like, well, if the running time of, let's say, L3, L4 is twice as fast, if, so I'm just gonna call these block two and block one. So if block two speed is 2x block one, then give block two 2x the data. So this is what we mean with like using mini batching in a like somewhat intelligent way here. But yeah, I mean, let's just keep going and see how they actually do it. Because like, I'm sort of jumping at, because this is stuff I've been thinking about a lot independently as well. So it has potential to give inter-worker communication can be limited to activations and gradients between adjacent layers assigned to different workers. And so we observe such communications to be up to 95% less than that for data parallelism training. So PipeDream is the first. I mean, so that's another thing, right? Like when you're doing a forward pass on a single machine, like it's not at all entirely clear to me like what gets loaded in RAM or what gets loaded in memory. But if everything can fit in either your cache or RAM, then the just by virtue of having the data be more local, like everything's going to be a lot faster. So it's the first system that combines pipelining model parallelism in an automated way. Into layer DNN into stages, which are layer subsequences that are each executed on a different worker. And it depends on both the model and architecture and the hardware deployment. So bad partitioning where stages uh, have widely skewed amounts of work and lead to workers spending significant time idle. Yeah, there's some nice diagrams of this later in the paper. I'll just show them to you later. So since the NS will not always divide evenly among parallel workers, PipeDream can use data parallelism for some stages. And so multiple workers can be assigned to a given stage, processing different mini batches in parallel. Third, unlike traditional unidirectional pipelines, DNN training is bidirectional. So the forward pass is followed by a backward pass to the same layers in reverse orders. So PipeDream interleaves forward and backward mini batch processing on each worker while making sure to route mini batches through the same workers on the backward pass. Oh, interesting. I see. Yeah, yeah. So same worker. Uh, I mean, and I will just do this as an important. So this help keeps all worker busy without pipeline stalls while preventing excessive in progress mini batches and ensuring model convergence. Fourth, weight versions need to be managed carefully to obtain the high quality model at the end of the training. We find that allowing the backward pass for a given mini batch to use more up-to-date parameters than those used in the corresponding pass can be a significant problem. PipeDream maintains parameter value versions for each in-flight mini batch to combat this problem. So experiments with PipeDream confirm its effectiveness, and they try it on CNNs and RNNs. And they try Inception, VGG, ResNet, AlexNet. So these are all like very popular CNNs. I think the details, as far as we're concerned, aren't too interesting, but I am just curious, like which ones end up becoming easier to scale. I would suspect it's the simplest one. I don't know out of all of these which one is like the simplest architecture. I know ResNet is the one I hear the most about. So to summarize, this paper makes four primary contributions. It introduces a parallelization across specialized DNN training to address communication bottlenecks by combining model parallelism with aggressive pipelining and data parallelism where appropriate. Second, it identifies the key challenges in realizing the performance potential of this idea and details solution for each. Third, it describes a system that efficiently implements pipeline parallel DNN training. Fourth, it experimentally demonstrates that PipeDreams allows parallel DNN training in circumstances where communication overheads limit data parallel training, including cases where data parallel is slower than single machine train. Like, when is this not the case, right? Like, I mean, I think this is, sorry. So this is also pretty important. Like, basically, um, if if your model is slow, you want to do data parallel. But then if you do data parallel and the communication costs are really big, then it's gonna just be faster for you to run it on a single machine that has like potentially infinite RAM and infinite compute. So I just want to write the note here, and I want to say data parallel doesn't scale for huge models. So a DNN model consists of a sequence of layers of different types, like convolutional, fully connected, pooling. So DNN models are typically trained using a data set of labeled images, multiple epochs. They take a mini batch, they have a forward pass, they have a current updates for next layer. The output of the last layer is the class, and then during backward pass, each layer computes the error of the previous layer and the weight updates for all relevant layers. Okay, so this goal can be captured statistical efficiency, the number of epochs needed to reach a desired level of accuracy, and hardware efficiency, the time required to complete a single epoch. Well, I would also add to this, like basically, I would add number three, which is hardware cost, right? Like, yes, like maybe you can get something that works like, 50% faster, but if it costs you 10 times as much, it's not really necessarily worth it. So anyway, yeah, let's look at this. Communication overhead as a percentage of total training time. Wow, how come ResNet's so much better? I hope they explain why. Same for Inception, but still, like, I'm just really impressed by Red. Like, these guys are crazy. Like, why? Even on the relatively slow K80. So two factors contribute to an increase in the communication overhead across all models: an increase in the number of data parallel workers and an increase in GPU compute capacity. All right. So here they talk about data parallelism. So with data parallelism, the input data set is partitioned across multiple GPUs. And each GPU maintains a full copy of the model and trains on its own partition of data while periodically synchronizing weights with other GPUs using either a collective or communication primitives or parameter service. Yeah, so basically this is back to this point here, right? How do these guys communicate the weights or gradient to each other? Either they do it centrally or through a server or directly to each other. And sort of the two like ways, like the two names for these paradigms are basically either like MPI, which is a message passing interface between processes, or it's going to be a parameter server. So basically you have some sort of central server that keeps track of the like, basically the latest weights or the, all the gradients, and then it just tells everyone, please synchronize from me. Everyone stops what they're doing, they synchronize, and then they keep going. So on one hand, synchronizing at the end of every minute batch, referred to as bulk synchronous parallel or BSP, reduces the staleness of the weights and it ensures good statistical efficiency. However, BSP requires each GPU to wait a stall for gradients from other GPUs, thus significantly lowering hardware efficiency. So despite optimization such as weight-free propagation, uh, where where weight gradients are sent as soon as they're available, common in modern parameter servers, communication stalls are inevitable in data parallel training due to the structure of GN computation and the fact that communication can dominate the total execution time. Yeah, so this is like especially relevant for large models. Like and it's sort of an Achilles heel, right? Because you only want to do data parallelism when your model is really slow. But all of a sudden, instead of like you've saved time on communication costs, but now you have to deal with these like insane. Sorry, you've saved time on computation costs, but now you have to deal with these ballooning communication costs. So so these DNN, they run on commodity public cloud servers. First, starting with slower GPUs such as K80, we know that some CNNs and sequence models for video transcription spend significant time communicating. So networks such as ResNet have comparatively low communication overhead. Second, as the number of data parallel workers increases, communication overhead increases for all models. Third, as GPU compute speed increases, communication stalls increase for all five. I wonder how do they measure this, by the way? Communication overhead as a function of time. So open question. How is communication cost measured? This doesn't have to be an open question. Let's just look this up. Communication cost measure, let's say principal. I mean, it looks like there's ways to do it, but it's definitely not it doesn't look like it's just out of the box like he's doing with the TensorFlow. I guess people are still figuring out how to do this stuff because like most people wouldn't run these large clusters. They like to say that they do though. All right. Um, so this is data parallel with 4 machines. Yeah, so you see here, like each machine has a whole copy of the entire model, which won't work if the model is very big. Even if it fits, there's still going to be really high communication costs, and if it doesn't fit, then you have to do model parallelism, which even has even more communication costs. And then for each one, it does the forward layer, it does the backwards layer, it blocks until everyone can synchronize. It looks like here, at least in the figure, they're making it seem like the communication cost is still less time than the time it takes for the forward and the backward pass. But regardless, like this may not be true for an insanely large model. Or if you're doing lots of data parallelism, right? Like if you're doing, uh, if there was like 10 machines, then you have to wait for all 10 to be done before you can start, and then that introduces the overhead. So I would assume like Cn is a big O number of machines. So Primark has proposed more relaxed synchronization models where each GPU proceeds with the computation as asynchronous parallel. Okay, yeah, sure. So a natural question you may ask is like, well, like, what if we don't need to synchronize any of this crap? Like, what if you could just let them all work completely in parallel, and maybe just do a synchronization like sometimes, or maybe just not do one at all. Uh, but but the problem here is that uh, like you are gonna end up with bad updates, like stale waits. So a lot of the machines are basically going to be doing effectively junk work. I'm not sure how people fix this problem. Does not reduce end-to-end draining time. Oh, interesting. Yeah, yeah. So they're actually saying this too, right? They're saying, well, you can uh, like basically async updates are still very slow to get good accuracy. It's like it sounds good on paper basically, but then effectively when you try it out, the model performance is just like hot garbage. All right, so moving on. So model parallelism. So okay, yeah. So you have a model partitioned across multiple GPUs with each GPU responsible for only a portion of the model. I mean, yeah, I don't know why they say specifically GPU. It could be absolutely anything. It's just that, like, I guess GPUs are particularly suited for a matrix multiply. But I would imagine like model parallelism to work just fine for CPUs as well. Uh, so it works well for problems such as matrix factorization, topic modeling, linear regression, and it often achieves faster training time than data parallelism because of the improved statistical efficiency that arises from not using extremely large mini batch sizes. Oh, interesting. Yeah, so large many batch sizes reduce accuracy. So, but it results in severe underutilization of GPU resources as illustrated in figure. Oh, this is a great figure actually. Yeah, let me just show you this. So imagine that like here when you're doing a forward or backward pass, and then you have, let's say you have 4 layers and you have 4 machines. Right. So this is how you're supposed to read this. So so machine one does some work, does like a forward propagation, and then it passes those weights to like those gradients to not gradients, like activations to machine two. That passes it to machine three. That passes it to machine four. But while this is all happening, like at least until we've got the machine three, machine four is absolutely not doing anything. And the same shit's gonna happen when we're doing the backwards pass. When we're doing the backwards pass, where like machine four is gonna send something to machine three, and then that's gonna send something to machine two, and then it's gonna send something to machine one. So effectively, you have all of this dead time that's happening, and it doesn't really feel like you're taking full advantage of the fact that you're using four times the compute. So you're basically spending four times the amount of money to get very incremental benefits. Like, in fact, the only benefit you're getting is that your model fits, but you're not getting any sort of like nice speed ups. And so we want our chart here is that we want it to basically look all blue and all green. Like that's how we know that the utilization is good. And so ultimately, if you are writing a paper or you're trying to prove to yourself that the parallelism that you're doing is good, you would want to try to have a setting where everything is nicely filled up. Um, and I guess like the other aspect is like because they talk about this in the paper as well. It's like figuring out how to partition things is a hard problem. Like it's not like it needs lots of domain expertise, but it is something where like, well, because you can formulate it as a convex optimization problem, I think it would be really, really nice if eventually someone could just come up with a compiler and do this, at least for some sort of limited set of layers, like let's say dense layers or CNNs. Like I have a pretty good idea for how to do it for dense layers in general, like how to basically program that into compiler. But for other layers, I'm not too sure. I need to think about it a bit more. All right, so let's move on. So it results in severe underutilization of GPU resources. Each only a single stage is active at an instant of time. Pipelining multiple multi batches back to back would impose utilization, but it's traditionally not done because the bidirectionality of DNNs is followed by makes pipeline challenging. More importantly, a naive pipelining mechanism introduces weight updates, computations on stale updates, leaving to the final model achieving lower accuracy than state of the art. Okay, right. So this is sort of where stuff like unlocked pipelining becomes relevant. I think I'll do like another because that's its own topic. I'll just probably do another video about this stuff. So unfortunately, such online the site makes okay, looks at programmer recent work the reinforcement learning to automatically determine device placement for model parallelism. However, such online decision making are time and resource intensive. They don't seamlessly combine pipelining and model data parallelism. Yeah, basically the uh, yeah. So I'm just gonna say this like basically the optimal allocation algorithms are too slow. Oh, interesting. So they're also saying like, well, like another way to do it is just having like specialized hardware. So this is something we talked about like in the hardware lottery stream on Friday, 2 days ago. But basically, yeah, I mean, you could have your own hardware to do CNNs really fast, but you know, it's just going to be very expensive, and it's not obvious that like CNNs are just going to be the defining, way to do image just for the next like I don't know 20 years, at least 5 years. So if it's not at least relevant for another 5 years, 3 years, or 3 to 5 years, it makes the economics of actually investing in your own custom hardware to do CNNs sort of questionable. They have another way. There's one-bit quantization techniques. They have more implementations of all reduce to reduce the amount of data being sent over the network, to reduce the overhead of communication, synchronous communication patterns resulting in small network stalls that only slightly alleviate the communication bottlenecks. Okay, yeah. So basically, there are workarounds, but they're not great. It looks like. So PipeDream combines the traditional data parallelism with model parallelism enhanced with pipelining. So we call this scheme pipeline parallelism. So in this section, we first describe PP, and then we describe PipeDream's design that addresses the challenges associated with making pipeline parallelism training work efficiently. All right, so what's the difference here? So, okay, it looks like they have 3 layers, and then in the last layer, sorry, the last machine, they have 2 layers instead of the just one. And then what's happening is that we have the forward and we have the backwards pass. but then we also have the sync happening at the same time, right? And so this is going to look much more filled. And then I guess the challenge is to say, well, why won't the weight updates be wrong? And then, like basically, yeah, let me just write these down. So, stale updates, and then the statistical efficiency. So, as in, like, why is this important? Because if it takes you too much time, uh, like if it takes you too much time to get a really good statistical efficiency in this pipeline domain, then it makes like the benefit very incremental, because the whole reason we're pipelining is because we want to get speed ups. But if we're not getting them because converging from a machine learning standpoint is taking too long, even though we're computing lots more flops a lot more quickly, then it sort of makes this very pointless. So yeah, this is interesting. So you'll see here, like so this is the VGG model. Like yeah, this is what I was saying earlier, where the early layers are way larger than the late layers. So if you just partition them based on layer number, the model is just going to be painfully slow. All right, and so ensure no GPU is idle at any point in time. We inject multiple mini batches into the pipeline one after the other, and then we enhance model parallel with pipelining. So on completing the forward pass for mini batch, each stage asynchronously sends the output activation to the next stage, while simultaneously starting to process another mini batch. Okay, so this is the core algorithm. So I think that so this is, I'm just gonna write this down here, like, and I'm just gonna say, hey mate, do you mind sharing the paper's title here? Yes, of course. Uh, so the paper is called PipeDream, Fast and Efficient Pipeline Parallel DNN Training. Um, and so, yeah, it's an amazing paper, I think, like, because I read lots of papers that were sort of trying to describe the differences between model parallel, data parallel versus pipelining. I thought this was the briefest, and that's why I decided to cover it on stream. There are other papers. I don't know. Maybe I'll just write my own at some point, because I think all of these papers are sort of touching parts of the problem, but no one's sort of like creating this nice comprehensive theory for how do you fucking actually scale large models? Like, how do you make them like gigantic? Is there sort of some sort of like checkbox that you can follow and say, okay, my thing's too slow or it doesn't fit? I need to do this, then I need to do this, then I need to do that. I think at this point, it's lots of heuristics that are in people's heads. Um, that said, I mean, this work is addressing this, right? So pipelining communicates less because instead of having to communicate all the parameters, each machine has to only communicate the output data of one of the layers. So this often results in large reduction in communication, 90% for a BTG, right? So this is benefit number one. And it overlaps computation with communication. So while pipelining by itself reduces training time compared to data parallelism, we observe model parallelism and data parallelism to actually useful. I'll also, the paper is called Pipe Dream Efficient Fast and Efficient Pipeline Parallel DNN Training. So a bunch of other things. All right. So PipeDream aims to combine pipeline model parallelism in a manner that minimizes overall training time. Uh, but there's sort of a few key problems, right? So automatic partitioning is sort of a hard problem. Ensuring is effective in the case of asynchrony, and scheduling. Thank you for the subscribe. Appreciate it. So just let me know if you have absolutely, any questions about any of this. I'm happy to, explain it in a painful amount of detail. But appreciate the follow, you Sultan. Uh, so yeah, so we have this automatic partitioning of work across available compute resources. So how do you split up your model? How do you schedule the computation to make sure that the model isn't bottlenecked at any one point? And how do you make sure that what you're actually learning isn't garbage, given that the blocks are making updates asynchronously, and that a block that's faster is just going to be going through more data. And so it's just going to be way more up to date relative to the slower parts of the model. So, how does this all work? So, given a model and a set of machines, PipeDream's first job is to automatically partition layers of the model so to minimize training time. And so, this is the workflow they've done. So, stage one, pipelining model and data parallel training. So they have a profile. Okay, yeah, I mean, that's what I figured. Like they have some sort of compiler that comes in and does this stuff. So they do number of machines, PipeDream optimizer. Oh, okay. Well, this isn't terribly complicated actually. So you basically do let's say like a run on a couple of epochs, and then just do basically some sample runs on model to figure out which layers are slow versus fast, right? So basically, after every layer, you go, this is how much time this took. I think you can do this with callbacks with something like TensorFlow. So just like it's asynchronous communication, computation that happens, like where every time a layer is activated, you go like, okay, this is how much time it took. Or you could just come into the core TensorFlow core base or write something like this, or just create your own library. There's sort of a couple of different ways I think you could go about solving this problem. So when partitioning layers into different stages across machines, so PipeDream's partitioning algorithms must ensure that each stage roughly performs the same amount of total work. Okay. So load imbalances make everything slow, correct? Profiles, profiling the DNN model, the size of the output activation. Oh, interesting. Okay. Total computation time, the size of the output activations of the layer, and the size of the parameters. Oh, okay, interesting. So we're looking input size, output size, training time. So sorry, activation time. With these three things for all of the layers, you can figure out like how to effectively load balance the layers across machines. The amount of data communicated per worker in a data parallel configurations with M machines is 4 times that is used to estimate the time for await synchronization. Oh, I actually like this formula. Okay, let's just look at this formula a bit and think about it. So we have, okay, so we have M minus one, so that's the number of machines. So the amount of data communicated is proportional to the number of machines, right? And then I don't know where this 4 is coming from, but let's skip it for now. Times WL, so what's WL? WL, I think it was here. So the size of the parameters of the layer per worker. Oh, I see. So M times WL divided by M. I would have just thought it's WL times M. I don't get where this 4 times M minus 1 is coming in. I mean, I would have also said it's WL times M, not WL divided by M. Anyway, what's big W though? Should be the total computation time, I guess, or the total amount of communication in the whole network. Okay, so the partitioning algorithm tries to minimize the overall training time of the model. So for a pipeline model, is equivalent to minimizing the time taken by the slowest stage of the pipeline. So this problem has the optimal sub-problem property. A pipeline that maximizes throughput given a machine count is composed of sub-pipelines that maximize throughput for smaller machine counts. So we can find the optimal solution to this problem using dynamic programming. So let AJM denote the time taken by the slowest stage in the optimal pipeline between layers 1 and J using 1 to M machines. So the goal of our algorithm is to find A and M and the corresponding partitioning. Okay, so wait, what's IJ again? So AJM denotes the time taken by the slowest stage in the optimal pipeline between layers 1 to J using M machines. Oh, I see. Okay, okay, okay. Got it. These are cool formulas, actually. All right. Okay, so the formula they then give it looks something like this. Very interesting. Okay, like I think the details of this formula aren't too relevant for today. But let's just take it at face value that this is uh, that you can figure out how to optimally allocate different layers on different machines by uh, solving the subproblem. And then the total number of subproblems is big O and M. The time complexity is also leading to a total time complexity of big O n squared M. So what's big N? What's big M? Through M, the total number of machines, and then total number of layers. So wow, n squared, M squared. As you know, this is not crazy, right? Because the number of layers, let's say it's gonna be, I don't know, at the most, let's just worst case, like 100 times squared, sorry, 100 squared times 100 squared. Let's just see much is this? 100 squared. Okay, how many commas are there here? Okay, one. Okay, so it's sort of like 100 million flops. I think this sounds fine, right? Like this is um, like assuming this is like an insanely large model and you're going to be training it for a long time. Like the one-time cost doesn't sound that crazy given uh, what you can do these days with some of these machines. So unlike traditional unidirectional pipelines, pipeline DNN training involves a bidirectional pipeline. So the forward pass for mini batch starts at the input layer and the backward pass ends at the input layer. So as a result, each machine in the system has to make a choice between two options. Perform the forward pass for a mini batch, thus pushing the mini batch downstream machines, and perform the backward pass for a different mini batch, thus ensuring forward progress in learning. So a simple scheduling mechanism that always prioritizes forward work hinders overall progress as weight updates can be applied only once backward pass is complete. Similarly, always prioritizing backward work may periodically result in idle machines with no available work. So we propose a scheduling algorithm that eliminates these problems. So you alternate. Oh, I see. So basically, uh, like in each block, alternate between uh, forward and uh, backward. Okay, this is cool actually. Like, yeah, you would expect that if the same block is doing both forward and backward passes because it's just like a block, it's like a machine just owns a layer. It makes sense. Like, I mean, you want to make sure that both learning and the predictions are both happening. And so, yeah, you could have all sorts of complicated communication schemes, but just, taking turns, works just fine. So figure 8 illustrates this using a partitioning with no data parallelism. So if we observe stage 1 is performed after the updates on mini batch 1 are okay. Let's look at this picture, for example. So we first off, like, we have this forward pass happening, but then immediately as soon as machine 1 finishes the first forward pass, it starts off with the next data sample. Similarly for here with machine 4, you see here it's alternating between backward pass and forward work. This is a great visualization, actually. So to address this problem, so now we're going to talk about the stale updates problem. So they're saying to address this problem, we use two techniques. Weight stashing maintains multiple versions of the 8, one for each active mini batch. After completing the forward pass, PipeDream stores the weights is used as part of the intermediate state for that mini batch. Uh, when performing the mini batch, the same version of weights used to compute the weight gradients. Okay. And so vertical sync eliminates the potential inconsistency across stages. For example, mini batch 5 uses parameters updated by mini batch 1 on all machines for both its forward and backwards passes. So this information is propagated along with the activations and gradient in the mini batch using stashed weight staleness. Okay, so let's see now the staleness point. So that we can formalize the degree of staleness for each of these techniques. For this discussion, we can assume a straight pipeline with the model split into n stages. The weights in each stage are represented as W1, W2, so on, and we denote the weights after T mini batches. So now after every mini batch, we compute the gradients averaged over all samples in the mini batch, and we have the following gradient update. With weight stashing, gradients in stage 1 are computed with weights that are n steps delayed. Gradients for stage 2 are computed with stage that are n minus 1 steps delayed, and so on. Mathematically, this means our weight update rule looks like W. Okay, important. So adding vertical sync alternates the weights to WT minus V, W1, T minus plus 1, T n minus 1 plus 1. U2. Yeah, I was gonna say, like, one of the reasons this confused me is this sounds almost identical to the BSP. Uh, oh, I see. Like, basically, there's a, yeah, I like this point. Basically, there's a degrees of staleness between weight sharing and model parallelism with BSP. All right, so now they're talking about GPU memory management. So provides the ML worker thread, pointers to CPU memory containing layer input data, parameters, and buffers for recording layer outputs and parameter updates. So PipeDream manages buffer pools, handle all intra and inter-machine communications. Oh, thank you for the follow, neural Turing machine. If you have absolutely any questions about any of this, just feel free to let me know. Glad to have you on board. So let's see. So far, like here, when it comes to all of this stuff, Um, like yeah, ultimate. Yeah, okay. So basically, what they're talking about is you need to synchronize your parameter server. You need to synchronize like the communication, and so they have some sort of central service that does this. So Figure 7 shows PipeDream's high-level workflow. Okay, data parallelism using synchronized weight-free backpropagation. Okay, great. How did they evaluate it? So I think it supports periodic checkpointing for fault tolerance. Sure. Uh, tails starting from the last epoch successfully trained by all stages. Yeah, it's just like because you're dealing with. Okay, so quick question, good sir. Where do you find these papers? I mean, how do you update your knowledge about data pipes and data ops? Scraping archive or some kind of hacker news for data? Okay, so I'm just gonna sort of reformulate your question. Like it sounds like you're asking me, it's like, how do I keep up to date and how do I figure out which papers to read? Um, I think like what ends up happening in my case is that uh, I would say in my early 20s, I would just look at what is hip and then I would just read that. The problem with this approach is that there is just like a mountain of papers being produced daily. And so what ends up happening is that you're constantly feeling like you're trying to stay up to date. Uh, and you're not actually learning or doing all that much because like people are actually producing full systems and you're struggling to just understand the basics of a paper at every point in time. So my advice has been is that I try to avoid reading papers unless they're at least like 2 years old. This has some problems. Like, I mean, when I talk with my peers, for example, they're like, "Oh, you didn't read this like latest new thing." I'll only read a new thing if it's like really relevant to what I'm doing at my day job, where I really want to build something on top of it. But if it's just to stay up to date for the sake of staying up to date, I've actually started avoiding this because it's a waste of time and it distracts me from actually building stuff or just deepening my understanding and stuff. So, quick advice is read papers that are at least 2 years old. That way, time does most of the filtering for you. That way, you're guaranteed to actually be reading something that is actually interesting and relevant. Whereas if it's something new, you're not actually sure if it's cool or relevant. Like maybe it's just hype. Maybe it's just like the writers of the paper are really good and they're convincing you that this is all great and all. But 2 years later, it turns out no one cares about this technique. So the funny thing is that if you do end up taking the slow approach, is that you end up like with not like an insane amount of papers to read, and it ends up becoming a lot more tractable. And so basically here in this case, like I've been for work looking a lot at different parallelism techniques. I skimmed about like I mean I have them here. Like let me show you. Like there's this paper I was reading. I was reading this paper as well. And then there was this paper and this paper. So this last one I did a stream about, like the hardware lottery. I don't know if you could see clearly, but so it's not too important. Like so, my point is that like I'll sort of focus on a topic, like let's say now it's been parallelism, and I'll just read everything I can. As a result, it ends up becoming way faster for me. That's pretty contradictive. Oh wait, what do you mean by that? It's like so. Oh yeah, so I'm saying I don't read a lot, then I'm showing you 5 papers. Yeah, so that's true. Like I think you're calling my bluff, but my point is that because they're all parallelism papers, it ends up becoming very easy for me to read them because like there's a lot of common nomenclature. These papers cite each other, so it's a lot easier. I don't need to go in and just like let's say I don't know, like people were talking about capsule networks for a couple of years. I've never even read that paper. I don't particularly care about it because I don't really have a strong use case for it. So I hope this helps. Um, but I mean, it's sort of a focus on a use case. I would say maybe I should summarize things for you. Focus on a use case. Make sure it's helping you either build something or it's helping you write a blog post or so focus on the outcome because I think staying up to date is extremely overrated in a field where you have hundreds of papers being published on archive every day. Use time as a filter and use your peers as a filter. Like, who are people that you admire? What are the papers they're reading? Read those. So if you do that cross section with old papers, you end up with not all that many papers to read. Okay, so they use two clusters. They use the NVIDIA Titan XGPUs with 12 gigabytes of memory, 64 gigs of RAM. So they use three different models, the VGG with 50 megabytes, Inception Net, that's great. They talk about, so pipeline data parallel implementation, pipeline dream versus data parallelism, one markers BSP, configuration, PipeDream speed up on one machine, 3x, 7x. Yeah, so wait, I thought Inception had less communication overhead. So, like, rather than reading on broad, vast topics, just focus on a particular topic and having knowledge about it. Uh, yes. So that's just like sort of. I learned this the hard way because I used to compulsively, obsessively read papers every day for about 6 years of my career. When I was at Microsoft, it's extremely overrated because you just don't end up producing anything. And I'm not saying like that means that like ignore stuff. It's more that like try to have an outcome, as in like summarize a bunch of papers, then write a blog post about it. Summarize a bunch of papers, make a library about it. Summarize a bunch of papers, use it at work. I think if you have this sort of attitude, it's a lot better. I think it's very tempting just because it feels like you're doing stuff. But what I've learned is that procrastination, sorry, like planning, is a sort of like the intellectual's version of procrastination, as in you're too intimidated to just start and actually make something interesting. So you read papers and you're like, oh, just one more, and then I'll start. But it's just, well, if 100 papers are being produced every day, when it's probably more at this point, then you're never actually going to get there. You're just going to keep reading papers, and then you're just going to be salty that people half your age are producing stuff that's a bit more interesting than the stuff you're reading. Um, so accuracy versus training time. Okay, we do not present end-to-end training on AlexNet. So okay, yeah. So they're saying here with PipeDream. Oh, interesting. So it reaches accuracy more quickly than a single worker. Okay, so that's good. In this case, a lot more quickly on VGG. Oh, I see, I see. Well, because in VGG the communication overhead is higher, that means like there's more potential benefits. All right, just one moment. What's up? All right. So with an increase in the number of machines, the communication overhead increases for all models. And so, okay, if you compare it to BSP, uh, what's ASP? Block sync. Oh, asynchronous parallel. Interesting. After every mini batch, so there's no synchronization. So they train a recurrent neural network. BSP training scales poorly. So value of data parallelism in stages. Model parallelism, straight pipe. Uses only one machine at any point in time. And hence is slower than single machine configuration. Straight pipelines. Conclusion. Pipeline addresses the communication overhead that bottleneck data parallel training of very large GNNs. So PipeDream automatically partitions and aggressively. Uh, no, no, not at all. Like I'm happy to answer these questions. So let me do this. Like I mean, like let me just sort of summarize this paper at this point, and then I'm happy to answer any more questions that you have about more of this stuff. So when it comes to parallelizing models, you sort of have three, like basically making large models scale, you have three knobs that you can turn. The first is model parallelism, the second is data parallelism, and the third is pipelining. Data parallelism is about having the same model deployed on multiple machines and then feeding it different subsets or full sets of the data to make it scale more quickly and not be limited by your RAM or disk bandwidth. Model parallelism traditionally is used in the setting where your model just doesn't fit. Like let's say your model is terabytes in size, let's say something like GPT-3. You can't fit that on a single machine. And so you'll have different subsets of the machine, of the model on different machines. and you'll be training those at the same time. The issue with this model is that because every layer is dependent on both the layer before it, in the case of forward propagation, and the layer after it, in the case of back propagation, you end up not actually utilizing these machines effectively. And after that is the problem of having different layers, just having different computational complexities just by virtue of their size. Like larger layers will take more time to run than smaller layers. And so instead of making these updates synchronously, we can introduce pipelining, which is a way to basically combine ideas from both data parallelism and model parallelism, where you can feed more data to the faster parts of the model and less data to the slower parts, make the updates synchronously, but still make sure that as far as a single batch goes, that a given worker is doing both the same forward and backwards pass with the same weights. And so these ideas combined together lets you take actual advantage of model parallelism and lets you use model parallelism as a technique to speed up your models and not only a technique to make your models fit. Uh, and so that's it for me. Like, I mean, I hope y'all enjoyed this. If you have any questions, like I'll sort of hang around. Otherwise, like I'll probably call it. But thank you so much for joining in.